Hello and welcome to this video on conservation of energy for GCSE Physics and Combined Physics, and don't forget to like and subscribe. The law of conservation of energy is one of the most important in physics. It is that energy cannot be created or destroyed, it can only be transferred from store to store. This means that the total amount of energy in a system at the start of a process has to be the same as the amount of energy at the end of the process. There cannot be more and there cannot be less. Energy transfers within a system, not all of the energy is transferred usefully. Some of the energy is dissipated. This is spread out so it can no longer be usefully transferred. This energy is sometimes called wasted energy, and it often ends up in the thermal store of the surroundings, which causes the surroundings to heat up. Within a closed system, a system where it's considered that no energy or matter can enter or leave, even the wasted energy has to be accounted for. The value for the energy at the beginning has to be the same as the value at the end. There can be no net loss or gain. So we can see on our energy diagram here, the input energy is equal to the sum of the output energies. So 2000 joules is our input energy, our useful output is 1400 joules, and our wasted energy from the kettle, and this heats up the surroundings, is 600 joules. 1400 plus 600 gives us 2000, so energy has been conserved, all of the energy has been accounted for. This is an example question using conservation of energy. This is a spring being compressed. At the start, the masses have gravitational potential energy. Assuming that no energy is transferred to the thermal store of the surroundings, the gravitational potential energy is transferred to the elastic store of the spring as it's compressed. Using conservation of energy, we can use what we know to calculate something that we don't, and this is useful. What we know that the mass is 300 grams, which is 0.3 kilograms. We know that the distance that the mass moves, which is 8 centimetres, and that's 0.08 metres. And we know the gravitational field strength of Earth is 9.8 newtons per kilogram. Using the equation for gravitational potential energy, which is m times g times h, we can work out the amount of gravitational potential energy in the store at the start of this process. So that's 0.3 times 9.8 times 0.08, which gives us our gravitational potential energy of 0.24 joules. We now know the amount of gravitational potential energy lost by the masses, which means we also know the amount of elastic energy gained. We now have the information needed to find the spring constant. The amount of elastic potential energy gained is 0.24 because this is the same as the amount of gravitational potential energy lost. This equals a half 0.5 multiplied by our spring constant multiplied by our extension 0.08 squared. If we rearrange that to make k, our spring constant, the subject, then we get 0.24 divided by bracket 0.5 multiplied by 0.08 squared. And this gives us our spring constant K of 75 newtons per metre. We can use the same idea for this example where a ball is falling and mass is given. At the start, the ball has gravitational potential energy and the amount can be calculated. Assuming that there's no air resistance in our system, the gravitational potential energy is transferred to the kinetic store. A ball of mass 0.056 kilograms at a height of 1.5 metres is dropped. What is the velocity as it reaches the floor? First, we need to work out our gravitational potential energy, which is mass times gravitational field strength times the height. And this is 0.056 multiplied by 9.8 multiplied by 1.5. And this gives us 0.82 joules. And this must equal the kinetic energy at the end of the fall. As conservation of energy has been upheld, all of the energy from the gravitational potential store has gone into the kinetic store. So now we need to use our kinetic energy equation, Ek equals a half mv squared. Substituting in our numbers, that gives us 0.82 equals 0.5 multiplied by 0.056 multiplied by v squared. Rearranging that for v squared gives us 0.82 divided by bracket 0.5 times 0.056, close bracket, and that gives us 28.29. This is not our final answer, this is v squared. We now need to get the square root of that to get v. So the square root of 28.29 gives us V, which is 5.31 metres per second. This is an example of use of conservation of energy. In this example of the ball falling, no mass is given. At the start, it only has gravitational potential energy. Assuming that there's no air resistance in our system, the gravitational potential energy is transferred to the kinetic store. A ball is dropped from a height of 1.5 metres. What is the velocity as it reaches the floor? In this example, no mass is given, so we have to look at our equations and make an expression that doesn't have mass in it. We know that the energy in the gravitational potential store is transferred into the kinetic store, and we know that no energy is transferred to the thermal store of the surroundings. And we know that the energy must be conserved. Therefore, gravitational potential energy, mgh, must equal the kinetic energy, a half mv squared. And this gives us our new expression. And in our new expression, you'll notice that mass is on both sides, mgh and a half mv squared, which means we can cancel them out. And now we can calculate the velocity without any value for the mass. We get gh equals a half v squared. Substitute in the numbers and rearrange for v squared gives us 9.8 multiplied by 1.5 divided by 0.5 gives us 28.29. The square root of that will give us v, which gives us our final answer of 5.31 metres per second. In this last example, we're working out final velocity on a slide. At the start, there's only gravitational potential energy. Assuming that there is no friction in our system, all of the gravitational potential energy is transferred to the kinetic store. So our question is, a person goes down a slide of height 8 metres. What is their velocity as they reach the floor? Explain what will happen to their speed if there is friction. So first we have to make our expression. We know that all of our gravitational potential energy goes into our kinetic energy store, so that gives us our expression of mgh equals a half mv squared. Mass is on both sides of the equation, so this can be cancelled out, and that gives us our new expression of gh equals a half v squared. We can now calculate the velocity without needing a value for the mass. Rearranging for v squared gives us 9.8 multiplied by 8 divided by 0.5 gives us v squared of 156.8. This is v squared and not v, so we need to do the square root of this to get v, our final answer. And the square root of 156.8 is 12.5 metres per second. If there is friction, not all of our gravitational potential energy is going to go into our kinetic energy store. Some of that energy is going to go to the thermal store of the slide due to friction. This means that less energy will be transferred into the kinetic store from the gravitational potential store. And as there's less energy in the kinetic store, then the velocity will also be less. And that's it for this video. Thank you so much for listening.